Good day, everybody. Welcome to today's webinar, which is Strategic Trenchless Rehabilitation Technologies for Water Loss Reduction. My name is Gary Wyeth. I'm the chair of the IWA Water Loss Specialist Group, and I will be facilitating today's webinar. First of all, just some housekeeping rules. This webinar will be recorded and made available on demand on the IWA website and the IWA Connect Plus platform for all IWA members. The speakers are responsible for securing the copyright permissions for their work, and all opinions, hypotheses, conclusions, and recommendations contained in the presentations are the sole responsibility of the speakers and do not necessarily reflect IWA's opinions. You will see that with the Zoom version that we're using here, we have two boxes at the bottom. There's the chat box, which feel free to use for general requests and general chat between people, maybe telling each other where you're from. And we have the Q&A box as well. So at the end of the three presentations that we're going to have, we will have a Q&A session. And so please feel free over the next hour to put your questions in the Q&A box, and then I will go through those questions and use those to quiz the panelists at the end. I just want to talk a little bit about IWA. So IWA is the global leader in water association with a vision to see a world in which water is wisely managed to satisfy the needs of human activities and ecosystems in an equitable and sustainable way. Hopefully, most of you know the IWA, which is why you're on this webinar, because you've received the invites. But the IWA is also made up of a number of specialist groups. And one of the biggest ones is the Water Loss Specialist Group, of which I am the current chair, and Anna Bochko is the secretary of the group. We have a very strong management committee with over 22 members from 17 countries, and we're very strongly supported with over 4,500 active members who receive the emailer that we send out every 2 weeks. You'll see at the bottom, there's an email address, and if you go to that email address, you'll be able to put your email in, and you will start to receive the emailers from the Water Loss Specialist Group every 2 weeks. The ISTT, the International Society for Trenchless Technology, is a non-profit organization dedicated to advancing trenchless technologies worldwide. The end of last year, the ISTT signed an MOU with the IWA, and there's already been one webinar, and this is the second one that's promoting the relationship between the two organizations. ISTT aims are to connect professionals, organizations, and industry leaders across the globe, provide resources, training, and events to support continuous learning, which this webinar is one of them, promoting collaboration and sharing of best practices, and driving innovation for sustainable and resilient infrastructure. If you need more information, you can email, you can see there's an email, info@istt.com, and they'll be able to give you more information about the organization itself and how you can get involved with them. So we have three excellent presenters today. We have Ari Gashi, who's the regional sales representative of Radlinger Primus Line, and she's going to be presenting on reducing water losses in aging pipelines using flexible fabric reinforced pipes, or FFRP, and she's going to show some applications and case studies. We then have Ivo Raphael Hemsing, who's the head of business development for Certex, and he's going to be presenting on water network rehabilitation using cured in place pipe, or CIPP, and an overview with references. And then our third speaker is Professor Mark Knight, who is the Chief Technology Officer of SIPP Americas. He's going to be presenting on advances in spray in place pipe, SIPP, pressure pipe rehabilitation technology developments and case studies. So without further ado, I will pass you over to Ari Gashi. So Ari is a regional sales representative at Radlinger Primus Line, as I've said. After completing her apprenticeship at the company, she's transitioned into her current role, supporting an international team across a variety of water main rehabilitation projects. Through this, she's gained valuable insight into challenges faced by network operators and project related work. And Ari will be talking about reducing water loss in aging pipelines, flexible fabric reinforced pipes. So over to you, Ari.
Well, thank you very much, Gary, for the introduction. And hello, everyone, of course, and thank you very much for joining today's webinar. As Gary said, my name is Ari, and over the next 20 minutes, I'd like to talk about one of the biggest challenges facing water utilities today, reducing water losses in aging pipelines. More specifically, I'll be talking about how trenchless rehabilitation using flexible fabric reinforcement pipes, or FFRP, can help utilities reduce physical water losses while extending the service life of existing assets. Before we even talk about rehabilitation technologies, it's worth taking a step back and looking at the challenges we're actually trying to solve. More than 30% of treated drinking water is lost globally before reaching consumers. That corresponds to roughly 126 billion cubic meters every year. That means that many utilities are dealing with aging infrastructure, as we just saw, that were installed like decades ago. Budgets are limited, pipe networks continue to extend, and of course, climate change is placing increasing pressure on available water resources. This means that reducing water losses is no longer just a maintenance issue. It has become an important part of sustainable asset management and long-term water security. So every job does really count. And now we ask, where do these losses actually come from? In the water sector, we usually refer to this as non-revenue water, or NRW. Simply put, NRW is the difference between the volume of water entering the distribution system and the volume that is actually billed to customers or consumers. Some of these losses are, of course, commercial. These include like inaccurate metering, and then, of course, billing issues or illegal connections. But today's presentation is going to focus on the physical losses like leakage, pipe bursts, or joint failures, since these typically represent the largest share of NRW in many drinking water systems. And hopefully that's exactly where rehabilitation technologies can make a real difference. So why do pressure pipelines fail, or pipelines in general fail? In reality, there's usually no single reason. Instead, several factors often interact over many years. For example, for metallic pipelines, corrosion remains one of the most common causes. Internal corrosion gradually reduces the wall thickness, while external corrosion attacks the pipe from the outside. Joint failures are another common issue, like ground settlement, installation tolerances, or aging sealing materials can all cause joints to lose their integrity over time. And then we have mechanical failures such as longitudinal cracks or sudden pipe bursts that are often triggered by pressure fluctuations or fatigue. And of course, external influences such as traffic loads, soil movement, freestall cycles, or even earthquakes can accelerate the deterioration process. So, as utilities extend or are trying to extend the service life of existing assets, we need a solution, or at least utilities are faced with a dilemma. So once leakage becomes a recurring problem, utilities are faced with this decision. Do they replace the pipeline completely or do they rehabilitate it? And of course, the traditional way with open cut replacement is a proven method. However, it comes with high excavation costs, of course, traffic disruption, long construction periods, and relatively high environmental impacts. For many utilities, especially in urban areas, these indirect costs can actually exceed the cost of the pipeline itself. And that's where trenchless rehabilitation becomes important, since it comes with minimal excavation, limited disruption, of course, fast implementation, and way lower environmental impact. So as this has brought us to trenchless technology, over the past few decades, this technology have become an established part of modern pipeline management, depending on the condition of the hose pipe and the project requirements. Different rehabilitation methods are available. Some solutions mainly provide corrosion protection, while others create a completely new structural pressure pipe inside the existing pipeline. But today's presentation is about the flexible fabric reinforced pipes. If you want to find out more about these technologies, I have this slide from the IWA website. You can look it up and you'll find many, many more. So, and as I already said, now that we've looked at the general concept of trenchless rehabilitation, we will look at FFRP. One example for this technology is the Primus line system, which has been used in drinking water, wastewater, gas, and industrial application all over the world. So now you ask, what does the system consist of? There are essentially two main components. First, of course, the flexible composite liner. And then we have the specially designed mechanical connectors. And together, these components form a structural rehabilitation system to carry the internal loads independently of the hose pipe support. The hose pipe becomes a conduit and takes the ground and also the traffic load. And first of all, we're going to have a closer look at the liner itself. Although I know it looks relatively simple from the outside, it's actually a carefully engineered composite structure. The outer PE layer protects the liner against abrasion during installation and throughout its service life. The real structural element is the seamless woven aramid reinforcement, or the Kevlar. This textile layer absorbs the pulling forces during installation and later withstands the internal operating pressure. Aramid fibers are extremely strong while remaining lightweight at the same time. In terms of strength to weight ratio, they're 10 times stronger than steel, which makes them ideal for this type of application. And of course, then we have the inner PE layer, which provides a hygienic surface suitable for drinking water applications, and it tightens the reinforcement against the transported medium. And together, these layers create a flexible yet highly durable pressure pipe. Okay. And that's not it with that. The system is currently available in diameters ranging from DN150 to DN550. Depending on the diameter, installation lengths of well over 2 kilometers can be achieved in a single section. And because of the wall thickness is relatively small, the hydraulic capacity remains high compared to other methods. Another important point is the pressure rating, of course. Depending on the diameter, again, operating pressures of up to 82 bar are possible. The system itself can also negotiate bends of up to 45 degrees without additional excavation. And in some project-specific situations, even larger bends are possible. Also, multiple bends. The product itself is referenced under ASTM F370825, which complies with 15 international hygienic approvals for drinking water. So, and of course, a rehabilitation system is only as reliable as its connections. And that's why connected technology plays such an important role as well. Different connector types are available depending on the application and the existing pipeline material, of course. Although the connector designs differ slightly, they all follow the same principle. It's to create a reliable mechanical connection while maintaining a leak-tight pressure system. This is especially important for drinking water application, where long-term operational reliability is essential. Also, the system is designed for a lifespan of 50 years. And in this cross-section, this gives you a better understanding of how our connectors actually work. The connectors consist of several individual components that work together. Sealing elements prevent leakage, of course, while the core and external sleeve securely clamp the liner between the connector. And the connector is therefore not simply attached to the liner, it becomes an integral part of the complete pressure system. So that's about it about the product itself. We will move on to the installation. Here you can see the installation in a graphic in a very simple way. One of the biggest advantages of trenchless rehabilitation is that the existing pipeline can remain in the ground, as you see here as well. Only relatively small access pits or points are required at the beginning and at the end of the installation section with a start and destination pit. Once the liner has been installed, then it carries the complete operating pressure independently of the hose pipe. The remaining annual space between the liner and the existing pipeline release the hose pipe from the operating conditions. So the hose pipe only needs to carry the external loads like traffic loads. Another important benefit is the possibility of very long installation sections of 2,500 meters. For example, river crossings, environmentally sensitive areas, and so on. Now we'll take a closer look at the installation itself. So the installation itself begins with the construction of two relatively small excavation pits, as I just explained. One serves as the insertion pit, so the start pit, while the other acts as the pulling pit, so the end pit. Compared with conventional pipeline replacement, the required working area is remarkably small. So especially when working in highly congested cities and urban environments, surgical pits are for daily life, like they allow for daily life to continue. So, and before any work, any rehabilitation work can start, the condition of the existing hose pipe must first be assessed. So we do have a CCTV inspection, which provides information about the internal condition of the hose pipe and identifies possible obstacles. The pipeline then is cleaned using scrapers and or rubber picks, as you can see in the pictures again. And after cleaning, the results are verified and documented with a second CCTV run, as you can see there after the cleaning. So, and once the pipeline has been prepared, the installation equipment is positioned on site. This mainly consists of the transport reel and the pulling winch, and of course the installation tools. The exact layout depends on the available working space and the project conditions. And the next step would be the actual liner installation. We use using a pulling head attached to the front end, as you can see there, of the liner. It is pulled through the existing hose pipe by a controlled winching process. Even pipelines containing several bends, as you see in the second picture, can usually be rehabilitated without excavation. And throughout the installation, the pulling forces are continuously monitored to ensure safe handling of the liner. Here you can see how the liner navigates through bends without a problem. So, and once the liner has reached its final position, it is inflated using compressed air with 1 bar. During this process, the folded liner gradually unfolds until it reaches the final circular shape, as you will see right now. And now we come to the final steps, or the final step. It's the connection of the liner to the existing pipeline. After the connectors have been installed, the complete system undergoes hydrostatic pressure testing, so we can verify its integrity. And for drinking water applications, the pipeline is also disinfected before being put back into service. Only after all these steps have been successfully completed can the rehabilitated pipeline be recommissioned again. Now to the most interesting part. So far we've talked about the technology itself, we've talked about the installation, but of course the most important question is, how does it perform under real project conditions? And therefore I'd like to show you some different parts of examples. We will start in Vietnam, where we had to rehabilitate a DN300 water pipe, or pipes, was actually 3. It was for potable water with a pressure rating of 6 bar and a test pressure of 9 bar. We used the DN300 liner, and it had a total length of 840 meter. Now to the project details. The situation was as follows. The DN300 steel water main was affected by corrosion. and required rehabilitation to secure drinking water quality and extend the asset service life. So the challenge was actually that the pipeline was located inside a bridge structure, and traditional pipe replacement costs would have been extremely high. So of course the solution was Primus line, allowing a trenchless installation with minimal disruption. Each trained contractor each liner section was installed in less than 1 hour by a local trained contractor and supervised by Primus Line. And the outcome was that the rehabilitation secured the drinking water supply, and it extended the pipeline's service life by 50 years. And it also was completed without excavation. We will move on to Spain. And by the way, congrats to everyone who rooted for Spain for winning the World Cup. So congrats. But now to the more serious part. We had to rehabilitate an asbestos cement trunk water main of DN 250, which had drinking water and a pressure rating of 7 bar. We used a DN 250 and a DN 200, and it had a total length of over 10 kilometers. Now to the project details. The 10 kilometers, or a little bit more than 10 kilometers, asbestos cement water main was in a critical condition since it was causing frequent pipe failures and water losses of approximately 25%. So the challenge here again was that the pipeline crossed environmentally sensitive areas, roads and railways, making conventional open cut replacement highly disruptive and environmentally challenging. They then decided to use the Primus liner in 20 trenchless installation sections, so we could avoid extensive excavation and reduced construction time. And as we all thought, the project reduced the construction period from 12 to 4 months, achieving up to 30% cost saving as well compared to open trench replacement, and we restored a reliable drinking water supply. Moving on to Germany, we rehabilitated a siphon with a length of 1,240 meters. It was installed inside a existing DN 300 P80 drinking water siphon beneath the Flensburg fjord. Again, for drinking water with a pressure rating of 10 bar, we decided on the DN 250, and it was installed in one installation section only with 1,240 meters. So the details here again. The siphon beneath the Flensburg fjord was installed in the 1970s, which is and was a key part of the city's water supply, and replacing the pipeline beneath the fjord would have been technically difficult and economically impractical. The challenge was to rehabilitate the existing pipeline with a single length, which we did. There was no possibility for additional access. We did a CCTV inspection, cleaned the pipe by pigging, and rehabilitated using the Primus line system. Of course, the liner was installed in a single pull and connected using the Primus line connectors. And it was also inflated with water instead of air. So the outcome was that at that time, this was the longest single Primus line installation in Germany. And installation was completed in 8 working days, with the liner pulled in within approximately 3 hours. And now we have the final project, or the last project, which was in France. It was a ground alongside on a street and 20 meter in a PVC pipe. stretching across a river. It was again for drinking water at a pressure rating of 10 bar. We decided on the DN 150, and we rehabilitated 1,340 meters, including the riverbed crossing in a PVC pipe. It was after a historic flood destroyed the riverbed and infrastructure in, I don't think I can pronounce that, but it was definitely in France. It disrupted the water supply, as you can see here in the picture. The urgent need to restore the drinking water to the flood damaged area, coupled with the difficult area, presented a significant challenge. So the Primus line system was used to install a free-floating pipeline across the riverbed and connect to the existing networks via land-based pipelines. So the outcome was that the water supply was restored to the affected area within 4 days without requiring any on-site hosting equipment. And that's about it. Thank you very much for your attention, and I'm going to give it back to Gary. Thank you.
Yep. Thank you very much, Ari. That was a great presentation. I think what we'll do is we'll wait until all three speakers have finished, and then we'll have the Q&A discussion after that. Just a reminder for all people on the webinar, please put your questions into the Q&A function, not the chat function, because we're not watching that, but please put it into the Q&A, and then I'll ask the questions later. So we're now going to move on to our second speaker, who is Ivo Hemsing, and he's the head of business development manager in the field of pressurized pipe rehabilitation at Certex Multicon. Since 2017, he has specialized in the planning and installations of global rehabilitation projects with CIPP. Since then, more than 400 installations with the Certex liner for pressure applications have been realized in over 30 countries. So Ivo's going to be presenting on water network rehabilitation using cured in place pipe, CIPP. Over to you, Ivo.
Thank you very much, Gary. Hello, everyone. Yeah, welcome to my presentation, water network rehabilitation using cured in place pipe, short CIPP. Today, I will first explain some of the basics of the standardized technology using GIP liner material, and then I will use plenty of construction site images to illustrate projects from my nearly 9 years as project engineer installing liners for drinking water pipes. Yeah, I'd like to start with something that's often reported in regional newspaper around the world. This fontaine was very near my hometown a few years ago and illustrates the impact that disruption in the water supply or in any kind of pipeline supply can have on big impact on people's life, the environment, traffic, and of course the costs. But let's take a step back. In my home country, Germany in particular, the facts clearly show that replacement and rehabilitation will become an even bigger issue. This is because large parts of the 5,300,000 kilometer long public drinking water network in Germany are already up to or incumbent 70 years old, and only about 1% of it is being renewed every year. Also, raw and drinking water losses in Germany at 5 to 10% is very low by the comparison globally. But experts estimate that on a per person basis, every German will need to invest approximately 10,000 euro over the next 20 years to keep water losses to 5 to 10%. So a lot of invest. Yeah, even though there are experts absolutely listening here right now, I'd like to share the top five most common problems that I encounter most frequently. You can see here in the pictures, there are damages due corrosion, joint leakage, cracking, structural deformation, and pressure surges, of course, also. And but since nearly everybody here in the audience is an expert, I won't go into further in detail. I just want to point out that these common types of damages or leaks in water systems can be rehabilitated using UV CIPP technology, resulting in a new estimated service life of at least 50 years. And also the host pipe material doesn't matter if it's PE material, asbestos, cement, steel, iron, it doesn't matter. As shown in the picture, liners do not require large chambers or excavation pits, and are very well suited for urban areas like cities, helping to protect the environment, trees. Project produces up to 70% less CO2 emissions than digging and installing new pipes. But first, I want to, it was too fast, sorry. First, I would like to classify this technology. That is UV cured glass reinforced plastic using this table in the standard ISO 11295. Due to the high mechanical properties like modulus of elasticity, resulting from the glass fiber in combination with the resin, independent and fully structural liner, which is then class A, with a very thin wall thickness is possible, which helps maintain the hydraulic integrity of the water system. Here is a graphic showing the construction or the design of the typical UV CIPP liner. This is here the Zatex liner. For drinking water applications, I will start from the outside and then move to the inside. Outside there is the damaged hose pipe, and once the liner has been pulled into the existing pipe and has cured out with UV technology, there's a thick PVC foil to protect the liner from UV light, like the sun, and mechanical stresses. And then an additional foil is used to prevent any resin, from escaping. To the blue one. Now, that is the most important one, the blue layer. There are well-engineered glass fiber mats impregnated with styrene-free vinyl ester resin. For UV GRP liners, the entire impregnation process is carried out in-house at the factory, so there is no impregnation directly on the construction site. The most inner layer is the thick PE and PA foil to ensure the best possible hydraulic performances. Tests. Of course, the pressure ratings or maximum operation pressures of GRP liners are very important for the network operators and owners. They are tested by certified party institutes, like here in the picture, the IMA in Germany, Dresden. On the right side, you can see a test stand. In the middle, there is the Zatex liner without any kind of hose pipe tested. It's a DN300 with a wall thickness of 6.3 millimeter. And first of all, this test stand there was 10,000 hours tested with more than 20 bars. And afterwards, they made a short-term internal pressure test. And you can see in the graph, after 200 seconds, the burst pressure was nearly 75 bar. And with all the safety factors and the reduction factors out of the standards and regulations, with that dimension, we have then a maximum operating pressure of 23 bar. Yeah, here we can see also the whole table, because the maximum pressures is depending on the dimensions. And it's completely based on the long-term internal pressures, so the 10,000 hours. We can make also project-wise specific wall thick calculations. So if there is a lot of groundwater, a lot of traffic over the pipe, we can also higher up the wall thickness to withstand all inner and outer forces. Here we can see a small selection of the key certifications, approvals, standards like the ISO or the IWA, and also the regulations. And my aim is to show you that while this is an innovative and new technology, yes, but it's also a proven and certified system. And I can confirm that my team and I have carried out more than 400 projects worldwide over the last 10 years. And to prove that, I want to show you a few case studies out of the past. I begin with a very easy one, I would say. It's in Germany, in Eastern Germany, in a small town called Torgau. This was a show construction site. We invited there more than 60 planners, network owners, operators. Everybody was welcome. It was a DM600 portable water pipe out of ductile iron. In the pipe sockets, the pipe was leaking with an operating pressure of 3.5 bar. The length was only 60 meter. But it was perfect to show our technology to everybody nearby. Like Ari told us before, first of all, we have to clean the hose pipe. It must not perfectly smooth and 100% round, but in total, we want to avoid sharp edges or obstacles inside. So we are getting robots inside, or pigs, or something else to clean, like water pressure, as you can see here in the picture. And then after cleaning, you can see on the left side on the truck, that is our Zatex liner H2O with the blue foil on it. It's getting right now pulled in over a conveyor belt, and it's getting pulled in due to a cable winch, which is on the other side of the section. Behind that, you can see also the UV truck, which is especially for drinking water. Here you can see this is the other side of the of the construction site. As you can see here, these two technicians are installing a so-called packer, which is a cylinder to save the compressed air inside the liner, and afterwards to get the UV equipment inside the liner to create out. But before curing and pulling the UV equipment inside, my colleague here is right now testing every part of the UV equipment. And only when everything is completely working, of course, we can, here on the right picture, getting the light train inside of the liner. And then together with the UV equipment inside and outside the truck, we have the full control. In the front and in the back, there are cameras. We have the full control before installing the liner. If there's any kind of obstacle or I don't know wrinkle inside, we will not start the installation. And also during the installation, we can see everything. Also, we have sensors for the temperatures and of course the operating pressure. To what diameter? This okay. See the diameter. It's up to 1,500 millimeter. But let's go on. Cutting back the cured liner. As you can see, the liner is now round and hardened. So a colleague now cut back the liner inside of the new piece of pipe. You can see here in the next picture. That's me checking the inner dimension, the new inner dimension of the hose pipe, checking the wall thickness. Everything was perfect as calculated. And then to make sure that everything is tight fit, we install a liner end seal. Many of you maybe know this technology. It's on the market since decades, and it's a pretty simple system. There is the black rubber material. This is EPDM, or other manufacturers have silicone on it. And then to make it tight, we install in total there are 3 steel rings which are pressed with a hydraulic expander to the liner and to the new piece of pipe there, to ensure that we have a minimum service life of 50 years. So that was in Germany a very, I would say, easy live demonstration of the liner. But now I want to show you some challenging project in northern Norway in the town Narvik. Very beautiful there, as you can see. This is a DN 250 section in total with a length of a little bit more than 350 meters. And the hose pipe was digged into the mountain with short relining. So we have to do it in one shot. That was very challenging, this 352 meter. And the hose pipe was ductile iron. And then the network owner or the customer was asking me, what is your maximum operating pressure with your liner? And I said, okay, it's 33 bar. And then he said, okay, then that is our new maximum operating pressure also in that pipe, especially for us. And the next challenge was the gradient or the slope. We had here a difference of the two entries of 101 meter, and so a slope of or gradient of 45 degrees, so 100%. I will show you later pictures that was really challenging. On the right side, you can see in that red circle what was coarse everything, because very new pipes had the EPDM out of the pipe socket. So every second pipe socket was leaking. That was, of course, not good for the pressure test. But then, of course, our liner is right now coming. As you can see, the gradient makes it quite difficult or challenging to get the equipment up to the mountain. The mountain in total was, I think, 650 meters high. And so our customer there used a sledge and pushed and pulled the UV equipment up to the mountain. And on the right, you can see the hose pipe, the ductile iron pipe, digged into the mountain. Yeah, also a very beautiful place there. Yeah, as you can see, we pulled in our liner from the top of the mountain. It was that was not challenging because it was like falling. Uh, and in the next picture, you can see after getting the air inside the liner, so the liner is completely close fit through the hose pipe. We cured it out. In the left picture, you can see we have the full control about the curing lamps. Every single lamp we can control. We can control the temperature, really nearly everything. And not to forget, the curing speed was 1.5 meter per minute. So everything was done in one day. And yeah, after the liner was cured out, we cut it a little bit back. And here we used in this project a new piece of pipe. We coupled that on with that coupling, and then we installed the liner end seal onto it, like in the last case study. And then the next challenge was to get back to to the town. And 1 week later, or on the Monday, there were the pressure tests with 35 bar. So that was also a challenge because on the blind flange down the down section was the total pressure of more than 17 tons. So a lot of pressure there, 24 hours. But everything was fine. So I was very happy. And yeah, now we had some a show construction site and a very challenging construction site. Now a very short one case study. What is normally, I would say, in Germany we call it bread and butter projects. This is 2.4 kilometer of DN1000. It was a handmade steel pipe with, I think nearly 90 years old. And we used a liner with a wall thickness of 9.3 millimeter. And as you can, see in the picture here, it's not only very urban and not only a lot of traffic, it was also a train station above. So, it was really, not hard, but we have to calculate very carefully. But 9.3 millimeter, due to the standards and calculations, was completely fine. And that's all from my side. Thank you very much for your attention. Yeah, and our title is also "The Future is Trenchless," I think which is quite good for this event here. Thank you very much.
Thank you very much, Ivo. Good timekeeping. So we will move on to our last speaker before we have the Q&A session. So our last speaker is Professor Mark Knight, who is the Chief Technology Officer of SIPP Americas, LLC. And he is a professor in the Department of Civil and Environmental Engineering at the University of Waterloo for over 27 years. And his research focus has been on pressure and gravity pipeline rehabilitation, asset management, trenchless pipe construction. And Mark's going to be presenting on advances in spray-in-place pipe technology, SIPP. So I will hand it over to you, Mark, now for your presentation.
Thank you, Gary, and thank you for everybody for attending. Spray in place pipelining, even though it seems relatively new, as I'll show you in a second, has been under development since the 1980s. And there's a variety of different terms now that are coming into the industry, which hopefully we'll be able to standardize soon. So SIPP can often mean spray in place pipe, which is the common term. In IWA C620, we call it spray in place polymeric linings because Different polymers can be used to be able to be sprayed inside the pipe itself. So in general, SIPP in North America at least refers to pressure pipe lining. Another term in the industry is sprayed applied polymeric linings. These have been used in culverts and other gravity pipes in those sections. So that's a little bit different, but the application is similar. Different types of materials are being used. So what we're really talking about is another alternative to cured in place pipelinings and CIPP, which Ivo did a great job in explaining and talking about. So even though it may seem relatively new with respect to some of the materials, this technology has been in development over the last 40 plus years. Really developed in the UK in the 1980s in order to be able to get rid of cement mortar linings that were having water quality issues. And they really wanted to um, fix that, and they developed epoxy linings that could be applied 1 to 2 millimeters thick. The issue was relatively slow cure of those. By the 1990s, they developed the first rapid cure materials, but again, they were limited in application to 1 to 2 millimeters, just basically as a barrier coat. And they started to be able to do same day return to service because they could speed up that curing process. In the 2000s, in the UK, they started to develop fast cure, high build applications. If you're familiar with the old 3M spray in place pipelining, that's where it came from. But there was also continuing development in the spray in place equipment in order to be able to apply those. They became computer controlled, and they developed with Yorkshire Water, the SteriCleanse system to be able to rapidly get a pipe disinfected and put it back in service. As we advance in the 2010, there's basically advances again in the spray equipment, innovation, and then abrasive stone cleaning came into the marketplace, which I'll show you a little bit later in order to be able to improve the cleaning and bond to the hose pipe. And one of the recent advances in 2019, Resimac developed the first aliphatic isocyanide polyurea, which is a fast-set polymer. It allows and has NSF approval to basically build a 1 to 14 millimeter thick liner quickly, 90 seconds dry to the touch. 15 minutes after you apply a coat, you can put a CTV camera in to get and build another coat applied on top of it with a 60-minute return to service. And by 2023, this material is now being used in the US, Canada, Australia, Chile, Europe, and now around the globe as a premier product. There are different polymeric resins that are available. We've got epoxies. The issue with epoxies in spray and place linings is relatively slow cure, and they're temperature dependent. The main thing about all these products, we have cure, which is important. We also have mechanical properties that we need to have. Some products have very good dry mechanical properties, but when they're saturated in water, over a period of time, they tend to soften. So we got to make sure that we have good wet mechanical properties is a critical point, especially for design of liners. The other issue is shrinkage. The higher the exotherm and the temperature of part A and part B, and when they mix, they increase that temperature. The higher that temperature, the more shrinkage that you get. So what happens is when you get in the aliphatic isocyanide polyureas, they kind of compromise and build that hot rapid cure ability to be able to do multiple coats without any prepping between the coats. It's got high dry as well as wet shrinkage, and the temperature exotherm is very low, so we can actually get bond at service connections as well as to the pipe. And this product was specifically developed for rehabbing of water mains, especially using the Shore spray equipment that was also developed in the UK. So the SIPP lining process is very different than CIPP. What we're going to do is we're going to use a hose pipe as a form to basically build a new pipe inside that pipe. So what we're going to do is use a spray rig where we've got a part A and a part B conditioned at the recommended temperature. And for Resiline 320, that temperature is close to 30 degrees Celsius. They're going to get pumped down the umbilical, and their temperature is going to be maintained, so the viscosity of part A and part B are the same. And then we're going to spin cast mix that material in a Y block, and I'll show you what that looks like. And then we are going to basically cast the pipe. So what we're going to do is we're going to get the spin head at the far end, and we're going to pull back the spray head and coat the pipe with the polymer with a thickness of anywhere between 1 to 3.5 millimeters of material at a given period of time. The air motor is driven by compressed air and runs at about 10,000 RPM. So the process is rather simple. So what we're going to do is we're going to take droplets of that material, and we're going to apply it relatively fast. So we can line about 150 to 160 meters. The umbilical length is what really controls the length of that material, and we can now build the lining thickness that you actually require on the inside of the pipe. So the process is relatively simple. Part A and part B come in and go through a Y block where they mix. So that's the first time they actually mix. Then they go through a static mixing tube so that they're fully mixed. And then they get thrown off as droplets onto that pipe wall. And the rig pulls back at a controlled rate. We constantly measure part A and part B flow to make sure that they're on ratio throughout the lining process, and I'll talk a little bit more about that as well. So a very simple process itself. The key to this process is to make sure that you've got the right equipment and the controls in process to be able to ensure that you're going to get a high quality lining. So the rig is a critical part of that process. Shore in the UK has been leading in innovation in the development of this equipment. It's a very computer-controlled piece of equipment. It constantly measures the resin flow. It measures the pullback speed of the umbilical. And we have the ability to do weight checks and to make sure that we're on ratio at all the time. So the equipment is very sophisticated, it's automated, and once it's programmed and it starts, it automates the whole process. From a quality assurance and quality control process, there's a detailed record that is recorded and provided to the owner, as well as to the contractor of weight checks, temperature of the part A and part B, flowback speed, and the lining thickness is applied. If during a lining application the material goes off ratio by 5%, then or more, then the warning is provided to the owner as well as the contractor to say, hey, we went off by 5% on ratio. If it goes off by more than 10%, the rig will actually shut down, and the operator cannot restart the rig until they go back and do some weight checks on that application. So quite a bit of quality control and operations is built into it. A lot of advancements in the rig. We have the ability to automatically open and close part A and part V valves. So if there is an issue, we can shut that material off and stop the lining. We don't need people in the pit in order to be able to start the lining. There's lining vision, which has a camera fitted at the end, so you can watch the the lining process go on live. And then we've got automatically set and forget lining. So the rig basically does everything, and the operator just monitors the whole situation. We also have non-contact flow meters and a smart weight check process to make sure that we've got integrity, and so people can't cheat the process on the lining process itself. So for larger diameter applications, we can do anywheres from 100 millimeters to 2,300 millimeters in diameter pipes. That's 16 to 92 inches. When we get into larger diameter, we can go to a power trolley instead of that spray head that's being pulled by the rig. So this is an automated system that's auto-powered. And in this case, we can do longer lengths because the umbilical is much longer. So we can do lining lengths here up to 400 meters in length. If we can get inside the pipe and collect the material, then we can have pits to pit it at around 800 meters, basically by lining one half of the pipe one day and then coming back and lining the other half of the pipe the other day. In lining projects, pits are expensive, and if you can reduce the number of pits, you can have a huge impact on the project cost itself in those sites. With respect to design for SIPP and CIPP, there's really no difference. We use the same design equations, same material properties developed using the same ISO and ASTM standards. What's really different between SIPP and CIPP is the construction method. We don't have to wet out a bag. We don't have to install a bag. We can just apply multiple coats on those applications. In North America, most of our contract specifications are construction-based and not performance-based. If you really want to use SIPP, then you should really use performance-based specifications on that application. What's really unique about ResiLine 320 is we have an 8-hour recoat window. So what does that mean? If I apply a second coat within 8 hours, you will not see a seam between the product. Will basically make a homogeneous thick pipe. So again, I can go between 1 and 14 in potable water networks. If it's raw water, we can go beyond 14 millimeters in lining thickness itself. This excellent intercoat bond seam, I don't have to do any prep to the liner as long as I apply that second coat within that 8-hour window. So that gives us a lot of flexibility. When we get to 10 inches, which 200 millimeters and above, we can apply 3.5 millimeters per coat. The 14 millimeter approval is 4 coats at 3.5 millimeters, so we can apply that basically in one work day, no problem. Mechanical properties are very similar to PVC, so we are basically building a PVC pipe. PVC pipe comes in specific dimension ratios or DRs. We can build the DR that you need in the field on that side. So we're very similar to basically building a PVC pipe with more ductility than PVC pipe has. So again, we have excellent long-term 50-year design properties. So there's no difference. We can design for 50 or 75 years. So we can meet ISO class basically 1 or D to B for sure. And in many applications, in some applications, depending on the issue that needs to be resolved, we can also meet ISO class A as being a fully structural liner. We've done burst testing on the materials, so 360 psi to 474 for a 150 millimeter diameter pipe segment, 3.5 millimeters thick. So that's more or less suitable for most municipal applications in North America. that are running at around 80 psi. So we can be anywhere between 2 to 4 times the operating pressure of the system. We'll never have the burst strengths of a Sartex liner that Evo was showing, but in many applications, we don't necessarily need that high strength. Service connections, we don't block any service connections. We throw droplets of material around that service connection and up into that service connection itself. And so we can recoat those service connections itself. So we don't have to block and open them up. If we do block them, we can open them up afterwards. We can also go through bends and turns. So this is a project in California where we had to go through 2 bends. So there's 2 coats of 3 millimeters, so 6 millimeter liner through those 2 bends. In this case, what we did was we did the first coat pulling in one direction, moved the equipment, did the second coat pulling in the other direction, and we've got a nice uniform coat at the joints as well as in the bend section. So we're going to make a watertight liner itself on that side. We can also clean hydrant leads as well. We can't coat hydrant leads, but there's often more tuberculation in the hydrant leads. And you can just see the material sprays up on the inside of that hydrant lead and basically cones. So from a case study point of view, in the fall of 2024, we did a project in Deep River. We opened up the pipe between 7 a.m. to 8:30 a.m. We started cleaning at 8:30. We finished cleaning the pipe at 12:30. I'll show you some pictures of that in a second. Between 12:30 and 1:30, we did what I call the CTV prep, as well as prepared the pipe for lining, basically making sure that all the joints were cleaned as well as the surfaces, and the pipe is ready for a high quality lining, and the light pipe wasn't lining them. In between 1:30 and 4, we applied 2 1.5 millimeter coats for a total of 3 millimeters in the inside of that pipe. And by 4 to 6 p.m., we had the pipe disinfected and reconnected, and people were drinking water on that pipe. So we didn't have to use any bypass. So it's a very quick and process. So there's the pipe at 9 a.m. That pipe had internal corrosion, didn't have any internal barrier. What we found was wall loss was up to 40%, no external corrosion. We drag scraped that pipe with a vac truck on the other end, so all the material went into the vac truck. Relatively easy and quick process. And then we used abrasive stone cleaning to remove any graphite on the inside of that pipe, and then we lined it with the 2 millimeter coats. We do bond to the hose pipe. We've done bond testing with coupons. We will well exceed 500 to 750 psi bond strength to the existing hose pipe. The main thing is that Resiline 320 has that low exotherm, so we get very little shrinkage on the pipe material itself. In Marina del Rey, we had to rehab a 1.8 kilometers of 18-inch or 450 millimeter water main. It was relatively deep with a high water table. We're right next to the ocean, and there were multiple bends in order to be able to do this project. Again, we were in a very crowded urban environment. We did lining lengths up to 170 meters at a given time, considering that the umbilical's around 180 meters for the rig that was used. There were many unidentified bends that we had to also take into account and line through. So one of the advantages is for us to be able to line through bends and not have any wrinkles and folds occur at those bends itself. And then we had the high tidal groundwater table back into service. So we just had to clean the pipe and liner the pipe, and the contractor absolutely loved the process and says basically it's a very very simple process in order to be able to be used in those applications. And again, this is the pre and the post lining image of, especially through those bands and the 6 millimeter installation itself. So some of the benefits, we can quickly construct a continuous, smooth, watertight lining at joints as well as at service connections. We can clean and line up to 160 meters in one workday, so it's extremely fast. And we can build the lining thickness that basically you require to meet your needs. So if we reduce construction time, public disturbance, we also will reduce project cost itself. So I'll turn it back over to Gary.
Thank you very much, Mark. That was very comprehensive. We'll go into Q&A now. We've got quite a few questions that have come in. I don't know if Ari and Ivo can turn on your cameras, and then we'll do a panel discussion.
Yeah.
So what was interesting, I think, with Mark's presentation was that with the spray lining, if there's any T's or any connections, it doesn't block those connections. So I'm just wondering, and we've had this question from a couple of people, Ari and Ivo, with your systems, what actually happens if you come across a T or customer connections? How do you deal with that? I don't know who wants to go first. Ari?
Ladies first.
Oh, sorry. Then I'll go first. Well, that always depends. But usually, of course, we should know that beforehand. We usually provide all, like the end client or the customer should provide all the information. So there is a possibility to connect the T's with the connectors. That's no problem at all. But we usually know that, like in most cases.
Okay. Ivo, anything to add?
Yeah, for the Zatex liner, I can answer that. There is a technology. We have a partner, Nuova Siria, in Italy, which are producers of these side connections of fittings. It's very new on the market, so right now limited for the dimension DN300, but it's possible, yes.
Okay.
So if I can add, in North America, what we tend to do with CIPP is to, before you install the liner, is to plug the services with a plug, and then install the liner, do your pressure test, and then drill out the plugs and drill out your connections or hydrant leads in order to be able to do those. So those are extra steps that have to go into that lining process with CIPP.
Okay. And the next question, I guess, is probably for all three of you again. What if the pipe that you're lining changes diameter or even changes material? How does that affect the process that you deal with? Can you just go straight through, or do you have to stop and at those changes?
Who wants to start?
Maybe we start with Ivo this time.
We can the Datex liner can be produced millimeter wise. So normally we are searching for the smallest point of the section we want to rehabilitate, and then the liner has a calculated stretching on it. But of course, when there is an annual gap between, we can also calculate that. So maybe then the liner will be a little bit bigger or thicker. But of course, it's we must decide it project wise.
Okay, Mark.
We can account for diameter changes. So because we're throwing drops of material, we can put the skis and the spread on springs so that we can change diameter. I've got a project where it's an 18-inch and goes to 17-inch. So I can do those diameter changes. We just need to make sure that if we want an even application of the material, that the spray head is centered in the middle of the pipe. We can even do a center